All right. Thanks for the introduction, Sergey. So yes, today we'll talk about these autoencoders and or encoder decoder in electron microscopy. So let me go ahead and get started. So one of the good systems to effectively play around with this is these complex nanoparticle arrays in different geometries. So I'll be using this, it's a code-doped indium oxide nanoparticle with tin and fluorine. So it's not so important, but what it is important is that the tin can tune the plasmon resonance by supplying additional electron, and it also tunes the geometry. So all we care about is the shape of these particles and the organization of the particles, and of course their response that we see through eels. The response could be, or the property could be, it could be anything. We're just going to use eels because we have access to the low loss spectrum here. So there are a variety of different configurations that you could imagine. When this sample is created, I believe it's intended for it to be effectively some continuous sheet or film structure, as you might consider this. But there are many so-called defects or other geometries that are also present. And so can we learn something from them, actually? So all these different geometries are present, and we have access to seeing some sort of response in space with the eels. And so this, yes, so what kind of different response will the eels look like at different locations, and can we learn something about the system? So I'll start off by saying, okay, well, we can measure a spectrum image or collect a spectrum image. In other words, we collect an eel spectrum at every pixel in some region, and then we can analyze that in a number of ways. The traditional way is to integrate some energy band and then display that. So these are the simple ways of analyzing the data. There are other ones with dimensionality reduction, which I'll show in a minute, just to kind of understand it, but we're really not understanding anything between the geometry and that resulting response. So one of the ways to do this, well, the first way to kind of understand this in a very preliminary fashion is kind of, okay, well, if either we put the beam here, or we've already collected the data and now we're looking at some spectra from a region that we choose, say the center of this hole, we get this spectrum. If we look at the particle, we get a different spectrum, and there are completely different spectra depending on where we are when we're looking. Of course, it's not terribly surprising, but how do we formulate this into some kind of relationship that we can understand better, and potentially that the machine can understand in a little bit more detail? And again, what I mentioned is, so we can do the NMF or PCA, any type of these dimensionality reduction techniques. They can pretty nicely show you what's present, but again, don't really tell you anything about the relationship between the geometry that you have and the actual spectrum. So this is really a nice way to explore the system, but there's not really any physical intuition that comes out of this. And again, no relationship is established here. There are other ways. I'll just briefly mention the multi-layer perceptron and autoencoders, which will actually use a version of this to understand this. But again, there's no relationship. We can understand this might be helpful for separating out responses and where they are in space, but again, no relationship to geometry or local geometry. Okay. So let me get to the actual interesting part here. So this is going to be done on a pre-acquired hyperspectral data set. So in other words, this image, when we collected a hyperspectral eels, we get for free the structural information to go with it. And so this is something, this is the structural image that we get from the eels data set. And meaning at every pixel in here, we also have a spectrum. And so what we can do with this data set, this three-dimensional data set, is create kind of image patches at every coordinate in here. And the image patch size is shown here by this box, but that's a parameter of our choosing, and that actually can affect our outcome. But anyway, we'll get into that later. So the image patch and corresponding spectrum. So in other words, the spectrum is coming from the center of this image patch. And so we'll just sweep this across the entire data set, and we'll get a pair of these at every pixel. So we have some kind of spatial descriptor and a spectral descriptor to go along with it. And we repeat this, at every pixel. So we can start to understand, okay, maybe we can stack up all of these things and have all these different spectrum and different images, but now how do we kind of technically do that? So this is where we go into this encoder decoder or autoencoder. In this case, we're sending a stack of the image patches or spatial descriptors as our features. So a stack of these patches here are going into our autoencoder through our encoder layer, condensed into this latent space to see if we can learn something, and then decoded back into our known target. So we have, we know what this patch here, we know what the spectrum looks like because we've acquired everything beforehand. Okay. And so we do that a bunch of times, by tweaking all of the parameters of latent space and the encoding and decoding network. And we get some sort of result we can evaluate how well that performs. And so it's always checking itself, the best way it can compress these things into a latent space. And so then we can kind of look at how this looks in the entire space, the image space, how well we did with some sort of mean squared error, or what we could call uncertainty. So again, this top block looks like the following. There's something changed here. And so when we send in the features as image patches and the targets as spectrum, we're calling this Im2 spec. So it's fancy name, yes. And another way to kind of visualize what's going on here is that, the latent space is a complicated object, I would say. And a lot of times difficult to understand or visualize, but we can do what's called back projection or forward projection once we have this learned latent space to see what kind of things look like from the machine perspective. And it may not make much sense, but basically there are two latent dimensions in this case, 1 and 2. We can have more than that, but some kind of descriptor in space in one dimension and in the other. And you can kind of see that there are different image patches kind of blurred, not really blurred, but coming together. And so this is kind of, what this thing has learned. There are edge features, there are, more centered on the particle, there are corners and so on. And so there's a bunch of different so-called features that this is learning in this latent space. And then the corresponding spectral representation in the forward projection corresponding to these things. So that's kind of what this has already learned, some kind of relationship between these two things. And so again, we can look at the error for different number of latent dimensions. This is what L is. 2L means 2 latent dimensions. 10L means 10 latent dimensions. So we can increase the number of latent dimensions here to whatever we want. We won't be able to really see any of this or understand it unless we do it at 2 dimensions, just for human perception. There is a drawback to just putting more and more number of dimensions. Probably will make our things more accurate, but now we're kind of over describing the system in some sense. And so we tend to stick around 2 latent dimensions for the most part, but this is something to also play with. So after we do this training, again, I didn't mention this before, but we when we separate this hyperspectral data set into image patch and spectral pairs and send this into the training network, we don't actually train all of the data. We split it, standard train test split. And I think this is something like 85% of the data is used for training, and then the other, whatever it is, 10 or 15% is used for testing and to validate what this is doing. And so these image patches have never actually been sent to the network, so it doesn't have this as a reference. And so we want to use this now as, okay, now I'm going to give you this image patch and you tell me what the spectrum is. And so when we do that, we find that it does a pretty decent job. The ground truth is this blue one here, which, again, when we increase the number of latent dimensions, we can, get a better match typically. But in any case, it does a pretty good job in doing a spectral prediction, even at the number of latent dimensions equal to 2. So kind of what's going on is we're building this relationship, a library of relationships between the geometry. So there's different, geometries that you can imagine, and there's spectrum that is associated with it. And so idea is, can we do that, number one, in reverse? And because typically what we're interested in is we want a spectrum, and now we want to get that spectrum somehow. And so, in kind of an engineering standpoint, we want to peak around whatever this is, 400 milli-electron volts. Tell me what I need to build to get there. So that one is a little bit more difficult, but we can use the same scheme to kind of try and understand this. I'll mention there are limitations, of course, as with anything. This will not generalize for any particle system. And so this network, this relationship, is exactly designed for this chemistry of particles in this material system. It does recognize geometry differences, but it has no idea what the chemistry of these are. So if we have given this network the same image, but the chemistry is completely different, or let's just stick with that. That probably has a large impact on what the low loss EELs or plasmonic response of the system looks like. And so we have to keep that in mind. This is not just going to work for anything. But given that, it still does a pretty good job of this particular system. Again, this requires some pre-acquired training data. And as mentioned, if we want to do this in reverse, we need to have the capability to, design these particles in a geometry of our choosing. We're not doing that in this case. We're working with what we have, what I'm calling as fabricated systems. In other words, I mentioned these particles they're self-organizing in some sense. And so any of these edges or gaps are technically defects, and they're really not intended to be there in the first place. We're just taking advantage of the fact that they are there, and we can learn something from them. But if we find out that we need to create these particles in some strange geometry that's not here, what do? We'll get to that in a little bit. So to move on, as I mentioned before, so this is the same slide. The only difference is now, if we swap the features and the targets, can we do something there? And so now spectrum go into a stack here as features, and we're now learning something about that latent space and how, and then we know what the target is because we already have all of this. So same idea here. We're just reversing features and targets. In this case, the image representation looks a little bit more diffuse or blurred out a little bit more. So this was naturally a little bit more difficult to understand. And by the way, this is what we're calling spec to im, because again, we take a spectrum and we get an image here. Naturally, it's difficult to go from a one-dimensional space to a two-dimensional space with a high fidelity, but we can see what we can do anyway, in any case. Again, we can do these back and forward projections to kind of understand what this latent space kind of looks like from these spectral or image representations. And again, it's a little bit more diffuse in that sense. When we do this, we end up with some trained network, but we want to test it on, again, the features that have not been supplied to the training procedure. And of course, they're all very similar spectrum. I mean, even these four look pretty similar, but there are some differences. And so when we do that, we have the ground truth because we have all of this preacquired data. When we go ahead and do a prediction on that with using 2 latent dimensions, it actually doesn't do so bad. So in the first one, we're somewhere in the vacuum, or it's actually not vacuum, but off of the particle. And this can say it's some sort of edge. So it already kind of understands that this is an edge feature. And you might look at the spectrum and say, there's not really anything going on in this, let's say from 0.6 electron volts to 1 electron volt. There's some features that are present when you're actually on or near maybe an edge of a particle that's not here. So, okay, it learned something. That's great. And then we can look at the space between particles. Doesn't perform as well, in different geometries, but it does recognize that there's some kind of boundary between what's bright and dim contrast, for example. That's with the 2 latent dimensions. If we increase this further, again, this might be dangerous in the sense that we're over describing the current system, but we can still give it a shot to see what happens. It does look like it actually performs a bit better. And so, this is kind of an interesting thing. So again, this is system dependent, and it won't generalize to just any nanoparticle that you throw in here. And again, we're working with the as fabricated systems. So one of the things when we do this, you'll notice that I don't have, this is an energy axis here, and it looks like these are kind of noisy spectrum nowadays. So these were acquired a few years back on a traditional scintillator-based detector. And so there's a bit of noise in here. And typically, I think the number of spectral channels here tends to be, okay, if we include the low loss peak in here. So that's actually cut off and subtracted off. But it's total number of pixels in the energy axis is almost like 2,000. So do we really need that? And after subtraction and fitting the background, still left with something like, it's something close to 2,000 still. But do we need that many pixels or number of spectral channels is what I'm saying here? Probably not, especially if the newer detectors have a lot less noise. And so really, there aren't that many features in the spectrum here. And so probably can get away with a lot fewer. This will, help for training and so on. But also, can we even describe the spectrum by simpler means? Maybe a peak at certain energy. So we can take our spectral descriptor instead of an object of 1,000 or 2,000 different channels, and we could potentially reduce it to a handful, like 5 or 10 features that we maybe prescribe to the system to just simplify things a little bit more. And maybe something can be learned from that as well. So this is another outlook that we can think about. So to summarize this, we can kind of learn the relationship or correlative relationship between the local geometry and in this case, plasmonic response. So this can really be generalized to any, it doesn't just need to be, this is STEM eels, but it could be, cathodoluminescence in an SEM or even X-ray signal in an SEM or a TEM or anything really. As long as we have access to a structural image channel and some sort of spectral descriptor. Spectrum, again, could be X-ray, EOLs, CL, whatever, or even probably 4D STEM or diffraction, something like this. So that will work in most cases. Again, it will be for that system. It doesn't know anything about the details of the chemistry and all that. So you have to keep that in mind. So in learning something, so it's an interesting curiosity, I think, to learn something about these relationships. But now, and we can do this for the M to spec, and we can do it for the spec to M. But really, what are we trying to accomplish here? So one of the big pushes is, again, what I mentioned before, we have some desired spectrum that we want, and now we want to create that. That's difficult when we're typically dealing with something that's already here. As a microscopist, typically anyway, we're looking at what we are given by a sample grower. It would be nice if we could kind of bump that in the direction that we want, in the sense that we can do a little bit of the fabrication ourselves to get some geometry that we want, because we are dealing with, there's a lot of randomness in the particle geometries and how they're dispersed and so on. And I don't want to mention anything else here. Okay, one other thing I alluded to previously is this patch size. So in some sense, this is another, let's say, hyperparameter of our training in our network. But if we control the size of this, so in other words, if we make the patch much smaller, so the number of patches will be roughly the same when we do this. But if the size of the patch is smaller, we might be learning something. Just imagine this patch here as being much smaller. It's ignoring all of the kind of longer range effects. And so we could probably tune what we're learning, long versus short range effects, based on our window size. And so we can have some kind of, we can learn different relationships effectively, potentially anyway, by changing this patch size. And so that's something that we can play with later. So again, this is just a summary. What we can learn from these latent spaces going from M to spec or spec to M, and we can learn, some kind of different representation from this latent space, and so on. But as I mentioned, can we actually do this engineering to make the particles exhibit these spectral properties that we actually want? And the answer is yes, with some caveats. So because we are in an electron microscope, we have a lot of electrons potentially that can be present. We also can change beam energy from maybe something like, probably actually lower than 60 kV now. I think it goes down to 20 kV, maybe up to 200 kV. Of course, this depends on vendor and system and all of this. But the point is, in principle, practice might be a little tricky, but in principle, we can change the accelerating voltage and increase current, for example, to do, things like this, where we can use the beam instead of to measure the yields or measure or observe changes. We can actually use the beam to completely destroy certain particles that we want. So this was done manually by just parking the beam, let's say here, and then kind of just dragging it along. This is a kind of time-consuming process, but it's still possible. And so we can carve out part of a particle, different complex shapes, confuse them. So the point is, there is a possibility here to engineer the particles geometries that we do want. And so all of this was just done by bumping up the accelerating voltage and the current by current maybe by an order of magnitude, and the voltage from, I think, 60 to 100 or maybe 200. All of this still happens even at the regular operating conditions when we collect a traditional spectrum image in an EOS mode. If we do park the beam in one location and just leave it there, either by accident or not, we will start to change the structure. It's just much slower. And so one of the things that we want, you might even want to do, just collect the spectrum image of some location, and then just keep doing that in time to see how this structure evolves under the electron beam. So there are a lot of things that you can start to imagine, but particularly here, yes, we can create the shapes that we want right inside the microscope. And of course, there's some, maybe non-idealities that I would say is there's some maybe debris, like where does all the material go? Unclear, but this could be a potential route, is what I'm trying to say. And so then we could use that built structure property relationship library to guide our inverse design. And so to go forward, I showed everything here besides the last slide with the same data set. So idea would be to use not just one data set, but multiple data sets of the same material system with the same chemistry, so that we have more variation in particle shape, geometry, and so on. It did capture a bit of variation, and even in that one data set, but it might be better to do this with multiple ones, so we can just have a better, more comprehensive so-called library here, and potentially then we can start to solve this inverse problem a little bit better, given all of that. That kind of motivates this to on-the-fly type of experiments, which is a time for another lecture. So we'll get to that in a week or so, I believe. But keep this in the back of your mind that all of this was done offline. So could we potentially learn anything quickly on the fly? And so something called deep kernel learning, I don't know if that's been discussed yet or brought up at all, but it will be. And so that is something that we can use. And the idea is similar, where we're learning some kind of structure property relationship, except we're doing it a little differently, and it's done on the fly. And so with that, we can go ahead and start this collab, which I believe should be on the GitHub. And let me go ahead and stop sharing. Sorry?
Yep, so it's on the GitHub.
Yes. Did you have anything that you wanted to show, Sergey, before we do that? I don't remember.
So actually, maybe the way we can proceed is I can introduce the dual operational autoencoders, and then we can proceed with the collab.
Okay, perfect. Let's go with that then.
Okay.
I'll stop share. So
okay.
You can
so
go ahead.
Let me share my screen at this point. So Kevin have shown the beautiful example of using the encoder-decoder architectures in order to build a structure-property relationship. So basically, when we use the encoder-decoder, we start with the importing, taking our image object, compressing it down to the latent variable, and then decoding it into the spectrum. Or we can do vice versa. So we take the spectrum, encode in the latent space, and decode it back into the image. So it turns out that the great thing about the autoencoders and machine learning in general is that there is more than one way to solve the problem. And particularly the development of the encoder-decoder concept is the dual variational autoencoders, which we are going to demonstrate on the example of the mesoscopic data set. So here, the setting of the problem is the following. So we have the images of the gold nanoparticles. So same type of creatures as the indium tin oxide that Kevin have shown. So these particles can be resolved in the scanning electron microscope. So you see that they are partially agglomerated. So we have trimers, monomers, tetramers, another trimer, monomer, dimer. And you can also see that some of them have different shapes. So we have examples of the particles which are almost spherical. We have examples of the particles which are triangular. We have the ones which are hexagonal. This one, if you look carefully, it's actually formed by the pentagonal prism. So gold is actually shows pretty large variability in terms of the properties. And in this case, as you can imagine, that's a fairly painstaking experiment, but it is possible to find all these particles in the hyperspectral optical camera, meaning you can just take the optical spectra, and then you have the hyperspectral images like this one. So you can see that the complexity of the spectrum sort of depends on how many particles are there in the cluster. So if you look at the trimer, it can have so two trimer, number 1 and number 4. You can see that there are two peaks in the hyperspectral optical image. If you look at the monomers, so monomer number 2 and number 5, you can see that they have one peak. If you look at something more complex, like the tetramer number 14, you can see that there are also two peaks, similar to the trimers, but the shape of the second peak is different. If you have a more complex arrangement, like number 17, you see that the shape of the optical spectrum is also kind of different. So similarly to the examples that Kevin have shown, there is some relationship, and there should be some relationship between the number of particles in the cluster and their shape and the optical spectrum. So the difference in these measurements is that Kevin have shown the near field measurement. So you map the internal structure of the plasmon and how the plasmon modes are distributed across the particle. So in this case, we're showing the far field behavior. This is what you will see if you look at this particle from the distance. But there is one very big difference between the optical measurements and the SEM measurement. So for SEM measurement, we have to find each particle and zoom in on it and determine its shape. So that's a lot of work. For hyperspectral measurements in optical microscope, all we have to do is to essentially put the sample and we get spectra for all particles at the same time. So the natural question is, can we somehow build the relationship between the particle shape and the optical spectroscopy? So the first thing we can try to do is to explore the internal structure of this data set. So that's always a first step in exploring any new data, and see if we can try to find out whether the particle is a monomer, dimer, trimer, or tetramer based on the optical spectra only. And the way that we can do that is by taking the normal variational autoencoder, so the same example I've shown in the previous lectures. And then you know the drill. We take the spectra of all particles, we train the autoencoder, we visualize the latent distribution, and then we look at the latent distribution. So in this case, we also have access to the ground truth labels because we have actually went through the effort of building of taking the SEM images. And you can see that in the latent space of the autoencoder, the particles kind of sort of separated. So you see that in this part of the latent space, we have the monomers, here we have the dimers, but then it gets much worse. So the tetramers are kind of spread all across this manifold. The trimers are kind of mixed with the tetramers and dimers. And more importantly, look at the numbers. So in this case, the Z2 changes from -1.5 to 1. So in this case, things worked. But Z1 changes from 400s to -400s to 400s. So in the language of the variational autoencoders, it means that we have the collapse of the representation for one of the axes. So our manifold is essentially one-dimensional. If you look at the latent representation, so if you go on the latent representation from left to right, nothing much changes. So in this case, this behavior, so that you don't see much change going from left to right, corresponds to the fact that Z1 has collapsed, so we don't expect much. Going from top to bottom, you can see that in this case, things kind of make sense. So on the top, we have one peak, which can be split a little bit. If we go down, you can see that the second peak starts to appear. So if you compare it with this data set, you can see that the second peak is usually indicative of having more than one particle in the cluster. But everything said and done, this worked somehow, but definitely didn't work very well. So let's try to analyze the structural data. So structural data is a different story because we now take the SEM images, we put it in the latent space, and then we look at the latent distributions and latent representation. So in this case, things are a little bit more promising. So you can clearly see that our ground truth labels are pretty well separated. So we have the monomers here, we have the dimers here, we have the trimers here, we have the tetramers and more complex objects over here. If we look at the latent representation, we can see exactly the same behavior. So you can see that here we have the monomers. If you go from left to right, then they become dimers, and then they become something more complicated. In fact, it almost feels like we can ascribe some meaning to the Z2 latent dimension. So it's not clear exactly what happens here. It seems to be some residual variation of the contrast, but it definitely did not collapse. It's actually one of the things that we sometimes encounter in this type of problems, that we definitely have the autoencoder that converged very well, and we don't have the representation collapse. It doesn't necessarily mean that we can easily identify the meaning of the latent dimension of the latent variables. Sometimes we can, sometimes we cannot. But anyway, in this case, things worked considerably better. Then we asked ourselves a question: can we extend this into Spec concept in order to build the relationship between the spectra and images in a more natural way? So remember that in ImtoSpec, we have to train two networks. So one that creates images from spectra and another one that creates spectra from images. And then we said, look, maybe we can actually combine this type of architectures and create the dual VIE network when we start with our paired data sets. So we have the pairs of images and spectra. We have two encoders, so they can have the same structure, they can have different structure, that encode our imaging and spectral data into the latent space. So here there are several ways how we can work with this latent space, and I will briefly mention it later. But after we encode in the latent space, we then proceed to decode it into the image and spectral data. So when we train this type of architecture, we essentially have four losses. We have the usual Kullback-Leibler losses for the autoencoder. We have a reconstruction loss associated with how well we reproduce the structural elements, and we have the reconstruction loss that associated with how well we reproduce the spectral element. So the trick here, which is actually exceptionally important, is that the structural encoder allows for the rotational invariance. In other words, you can see that this particle and this particle, they look similar, but they're rotated. So without encoding the rotational invariance, we would never be able to train this network. So there are ways to get around it. One may be to augment the data through rotations. Another way may be to manually orient each particle in a certain way. This is not elegant. So if you can do something through making the more well-defined network architecture, do it through the network architecture. If it is, for whatever reason, difficult or not possible, then you can do it through the data augmentation. So what happens in the latent space? So it turns out that there are several different ways how you can keep things together in the latent space. So the simplest one is just to force the structural object and the spectral object to have the same latent embedding. So in other words, we brute force the latent vector for the data set, for the image and for the spectrum to be the same. And then we decode from this space. This works, but it turns out that this architecture, at least in the few trials that we get, tends to be a little bit brittle. So it really doesn't want to converge. So it turns out that we can do things a little bit more elegantly, which is we can have the different encodings between the different encoding vector for the structure and properties, but we can impose some measure of similarity. For example, we can say that the latent distributions should be close to each other. So this can be realized as minimized scale divergence between the two, or any several other strategies based on the affine transforms. But basically what we do is, rather than imposing the rigid constraint to have our latent representations for image and spectrum to be the same, we try to keep them close. So we give the system some flexibility. And this is how it works. So this is the example of the latent space representation, so latent space distribution, sorry. So this is the, now we can plot the structural data and spectral data in the same latent space because it is the same latent space. So you can see that if we add the labels corresponding to the class, meaning the number of particles in the cluster, you can see that they all are kind of well behaved. So the points for the single particle stay together. Points for the dimers, trimers, and tetramers also stay together. They are not perfectly separated, maybe except for the monomers, but you see that they definitely kind of stick to each other. We can, of course, take this data set and look separately at the structural and spectral data. And you can see that the distributions are not exactly the same. So structure is more distributed, spectra is kind of more localized, but generally it gives us a feeling that at this point it sort of worked. Compare it to the example of the single VIE where the spectral data clearly collapsed. So what can we do? Then the next thing that we can obviously do is to look at the latent representations when we decode the particle shape from this latent space, and we can also decode the spectrum from this latent space because we have access to both of them. Again, this looks very well behaved. So on the left, we have the monomers. If we move from, sorry, on the right, we have monomers. If we move from right to left, you can see that we go from monomers into the dimers, trimers, and tetramers. More importantly, is that we start to have some idea about what happens in the vertical direction. For example, if we go from here to here, you see that the particle becomes more asymmetric, so these ones become triangular. If we look at the spectrum, we also see very clear, very well behaved dynamics. So we have the change in the spectral shape in one direction, change in the intensity and appearance of the additional peak in the second direction. Now, one thing that is actually very unusual here and was actually very surprising is that we deal here with a very small volume of data. So the principle in the machine learning is that you always talk about the big data. And one of the things about the big data is that you want to have more data points than the dimensionality of your data set. So obviously, if your data set is comprised of images which are, let's say, 40 by 40 pixel, meaning 1600 dimensions, a 1600 dimensional vector, big data would be sort of tens of thousands of the examples. Experimentally, that's way too much. So until we have a fully automated microscopes, we are not going to take 10,000 measurements by hand, and we are not going to be able to curate this type of data by hand. And even if we have automated microscopes, that's maybe not the most effective way to use their capabilities. So in this case, it turns out that we can train the dual encoder decoder with just 300 examples, which is really impressive because the number of the examples in this case is well below the dimensionality of the data set. So why it works is the difficult question. So I don't know the answer for that one. We can speculate that that's because the autoencoders are heavily regularized or what's not. But the important thing is that it does work. And this allows us to build the structure property relationship between the structural data and spectral data. Now let's look how it works in the real world example. So let's assume that this is our dark field hyperspectral image. So this is essentially the image that you get from camera. Notice the scale bar here. So this is optical image. Each blob is one of these particles, right? The monomer, dimer, trimer, tetramer, and so on. So the shape of the blob is Gaussian because the site of the object is very, very small. So this is just the optical resolution. And each blob contains the spectrum. So we can average over the blob and have the full spectrum. So now let's see how our dual VIE worked. So this column shows the ground truth, meaning zooming in on each of those objects in the scanning electron microscope and taking the picture of the particles. This one is the prediction. So this is VIE, dual VIE that was trained on the previously acquired data set. So it actually worked remarkably well. So look at this. So this is our ground truth 1 and 5. They're both trimers, and the network predicted trimers. This is 2 and 6. So one is the tetramer, another is monomer. So the network predicted the monomer remarkably well. Tetramer looks different. So of course, we don't expect to capture these details, and the number of examples for the tetramers is exceptionally small anyway. So this is a little bit more complex one. So this is number 3 and 7. This is a pentamer. This is a dimer. So in this case, things didn't work that well. So the pentamer become the tetramer, and the dimer also become the tetramer. You can notice that when it is off, then the quality of the reconstruction is also not so good. So the images start to have this weird kind of rays emitting from the particles, but it's not solid enough to be a predictive measure, but it's something that we notice. And then if we look at 4 and 8, so this is a monomer and dimer, and they were reconstructed at the monomer and dimer. So basically, it turns out that based on the optical spectra, which are very easy to measure, we can reconstruct the shapes of the particles, which takes kind of much longer time and much more effort to measure on the different microscope, which basically means that imagine that the same type of scenario when we want to study the dynamics of these particles, aggregation, any kind of the dynamic phenomena. So by now we would be able to detect it from optical measurements without the need for the high resolution or relatively high resolution electron microscopy. So that's kind of the idea. We, of course, can quantify this behavior further. So as usual, we build the confusion matrix for this type of problems, meaning that this is the true particle number, this is the predicted particle number, and you can see that the confusion matrix is actually not bad at all. So our monomers and dimers are identified exceptionally well. So there is a little bit of the mixing between the two. So the tetramers have about 60% recognition. Tetramers and higher are worse, but realistically for these ones, we literally have tens of examples, not hundreds. So we can, of course, explore this further. For example, we can try to confine our data set only for the monomers and dimers, so kind of artificially cull it a little bit. In this case, of course, things work much better, but this is also less interesting. So let me stop at this point, and I'm giving it back to Kevin, who is going to actually show how do this codes work under the hood.
There we go. All right. Thanks, Sergey. Whoops, hold on a second. Let me go ahead and share this screen. There's this guy here. Let's see. It's sharing, right? It's not showing that it's sharing. Are we good?
Yep, we can see your notebook.
Okay, good. All right. So this notebook, it should be uploaded onto the GitHub. There are a couple of things on here that I'll get to that are not on the GitHub, but will be uploaded after the lecture, but it shouldn't affect really anything that we're doing today. So this kind of describes maybe in a little bit more detail about what I've already described earlier. But note, you can find the paper on arXiv or on the actual journal that's related to this work for the stem eels, if you'd like to do that at some point. Anyway, so we can go ahead and just start running this. There are some dependencies, which just, straightforward NumPy and sklearn, things like that. Some function definitions, which are really for processing the eels data. And then the actual functions for encoder, decoder, you might be interested to look at that later, but for the sake of time, I'll save that for now. And so if we run this cell, we were just downloading, let's see, 4 different stem eels, hyperspectral stem eels data sets. And so this line will download it. So something with Dropbox changed where I had to, they're giving something with this RL key now. And so anyway, I figured a way around it. So we should be able to download this. If that doesn't work, please let me know. We can put up a Google Drive link or something like that as well. So once we download it, we can kind of load it and look at the structure. So there are four different data sets in here, and each of them have the HADF, or just the structural image. They've got the SINB, means spectrum image, no background. ENB is energy, no background, and then SI and E are just spectrum image and energy. And then some kind of pixel size for if you want to throw up a scale bar. So if we just look at the data, and we're looking at the if we average the spectrum images over all energy, we're going to see the following. And then if we just look at the HADF images, we will see the following. So notice that they're kind of the same. They almost look identical. They're not, because this is, well, you can notice some contrast differences. So we're summing mostly the zero loss peak is making these these images at the top. Anyway, not so important. The point is, we've got this hyperspectral data and the corresponding image. So if you notice, that second one here is what I used to describe or used as an example in lecture. And so again, we can do this nice thing here. Actually, this is data set number. I'd like to change that really quickly. We can change to whatever data set we want. For example, if we do that, it should look like the one from, maybe not. Oh, there we go. Thing here. Okay. Yes. Okay. So then we can start to integrate different energy regions. For example, this is the band that we're looking at. And again, that's the wrong one on the far end. And let's say we want to look at 4 to 5, 0.4 to 0.5 EV. We can change that, and it might look a little different. So in any case, we can play with that. That's just kind of standard analysis. We can look at this, okay, scale bar here, using that metadata of the pixel size. We can generate scale bar. So notice that, yes, this is much smaller than the optical images, or the SEM even. Well, actually, the SEM images might not be much smaller. Anyway, particle size around 20 nanometer, basically. If we do the NMF, we can cut some of the data. Okay, well, this is just, again, standard. We can do the screen plots. So all of these are the kind of this traditional unsupervised, machine learning, like they're kind of the first order, I would say, schemes that you would throw at your data, or just kind of PCA to look at the variance in your data, and then PCA or NMF, non-negative matrix factorization, to just visualize the data. And even these can take actually some time, and I'll just show really quickly. Okay, great. So there are different spectral components in the data. I'll mention that the NMF and basically all of these methods, PCA, all of this, don't have any, they don't care about the structure at all. So in other words, you're only learning the relationship amongst all of the spectra and nothing to do with the image. And so it's nice that actually they turn out to to show you very clear, locations on where these spectra are, but they don't know anything about it. And so in other words, you can shuffle all of the spectrum and you'll get the same result. So it doesn't matter from where they came from. It doesn't care about that. So the encoder decoder stuff kind of does. So we're learning that relationship. And so for the first part, I'm going to use what is called pyroved. And you can, run this. I don't want to run it again because it's already installed on this Colab here. And then some kind of utility functions or libraries as well. So pyroved is another one from, I don't know if Sergey has mentioned this, Maxim Ziadinov, who made this Atom AI, and a lot of the other Python codes, has also made pyroved, which is exactly for these encoder decoder style networks. So we run that. We can restart the runtime if we want. And we're going to start to create these image patches. And so again, looking at whichever data set we want, I'm tempted to just change this, but I know this works for at least this guy here. So let's just follow along with this one. So the first step is to generate some kind of image patches. We can describe or prescribe the window size here. This is just in pixels. And we're using these. These are originally from Atom AI. I just didn't want to have to install it just for these couple of functions. But basically, we're just getting coordinates at every pixel in here, which is just a grid, and then creating, patches and the corresponding spectrum from the center of those patches at every pixel. And that's just what this step does here. Optionally, we can do a step size of greater than 1. In other words, every other pixel, we can create a window. Maybe that would be helpful, but in some case, we want as much data as we can, and we want every pixel to be used as possible. So anyway, this is one of the parameters that we will be able to change. And so we could go, to 2 pixels, we can go to 32 pixels, but for here, let's just go to 16. That doesn't take too long. There is probably, it should have been done in the pre-processing step. So the data that has been loaded, where I have this no background, for example, here, the spectrum image, no background, and it does have the zero loss peak removed, but there's another kind of substrate background, which is so-called silicon nitride phonon, and these particles are suspended on some kind of membrane. And so that peak is there. The point is, I'm going to cut that off. It's about 200 pixels in the energy. And then I'm also going to rescale or interpolate the spectrum to about 1024 energy pixels. And so when we do that, okay, so all that means is, okay, let me just plot one of these spectra. If we look at it, it should look like that. So we've got about 1024 channels, or we have exactly 1024 channels, and we have 2,800 of these guys here. And we should also have that many patches as well. And so if we instead look at, well, I'll do that in a minute here. So this is just, next cell is to just reassign what we're calling features and targets. So in this case, for im to spec, our features are the image patches and our targets are the spectra. And so we'll do that here, and you can see the shape. Okay, the features are 2,800 of these, 16 by 16 images, and then targets are 2,800 spectrum. And then we can go ahead and look at this. So this is kind of more intuitive here. And so, okay, we have our overview image, and then we have this blue cross here is where, this is index, whatever, 120. So the image patch there is this, and the spectrum at the center of that patch is this guy. And so we could just look at that for every single one of these if we wanted to, but that's not really useful. So at this point, all we've done is take our spectrum image and corresponding structural image, which is acquired at the same time, simultaneously. And we've made a bunch of image patch and spectral pairs. Okay, we do some normalization and then split this into test and train. So test size is 15% here. So you can play with that if you want, but I wouldn't, probably not going to do too much here. All right, so now we start to use the pyroved. So PV is pyroved, and it's got the utilities to create kind of the train loader, just kind of initialize things. And then our input and output dimensions really shouldn't be specified here, I don't think, because we're already generating them. You know, this is going to be, this should be the same as window size, comma, window size. And this should be, the output dimension should be just the length of each spectrum. So that's what this is with the comma here. That's actually for kind of torch stuff. Anyway, okay, we initialize a model and then we start to train. So this is 100 epochs here. So if we start to train, so this is starting from scratch. Not too bad, actually, in terms of how long it takes. And again, that's number of epochs or epochs can be another parameter. I mean, you don't want to overtrain, but you know, can we get away with, you know, 10 or 20? Maybe we can start to look at the training loss here, which is printed. You know, it starts, you know, they kind of converging at around 447. It looks like. So I probably could get away with somewhere, I don't know, about 20 epochs. Probably will produce about the same thing as 100. In any case, it doesn't take much longer. I think we're almost there anyway. Yep. So that's already done. I'll note that this is already done because we are connected to this Colab GPU here. So that is one of the things. It should be automatically, the runtime should be enabled to be, where is it? GPU when you open this. But anyway, so that will, particularly for the training here, this will be a massive time improvement here. So in any case, if you notice that it's going very slow, double check that it's on GPU. So after the training, we can look at this manifold, which is kind of the spectral representation of our latent space. So we can see, okay, there are some spectral differences. A lot of them look like they're just peak intensity, but a little bit perhaps these other shoulders and so on. So that is a big part of the spectral signature, is the intensity of this low energy peak. In any case, if we look at the latent space, so we can encode our test features. Now we could look at all features or just the test features. In this case, just the test features we're looking at, and look at them in latent space. So this is very similar to what Sergey and I both showed earlier, where we have two latent dimensions and we have, you know, distribution of points in that latent space. Latent space here is described by 2 dimensions. We'll show in a little bit that it could be described by more. Harder to visualize and understand, but potentially can help describe things better. We can then cluster these points. In this case, we can do this by a number of methods. In this case, this is some mean shift. We could use also kind of a mixture model. Mixture models requires you to specify number of components. This one is a bandwidth here, so not so important, but we can cluster these points now. So, okay, that seems reasonable. Potentially there could be a 4th one down here. We could look into that later if there are questions, but in any case, we can cluster them. And then also look at the kind of the center of mass of each cluster and see what the spectrum from latent space actually looks like from the center of those. And so we can see, like, the points coming from green here show this much stronger, this green peak here. So that somehow represents this stronger thing here. So if we look at the spectral representation up here, all of these ones that have the strong peak are on the kind of the left side. That might be a coincidence that it's on the left side, but in any case, these are the ones that are corresponding to, you know, these points in latent space, because we're seeing the strong one here. And then we have 1 and 3 are a little bit weaker, maybe a different shoulder structure and so on. And it's just like, you know, looking at this in latent space can potentially be useful in that sense. And so what's useful now, though, is to look at all of those points, but in real space. So if we project them onto the actual system here, we find out that, okay, all of the green ones, which have very strong peak here, tend to be on either so this is not vacuum again, this is some background or substrate that, it's electron transparent, much thinner than the particles and weakly scattering. But that's what's causing these to be much stronger. So it already recognizes that, okay, if we're outside of the particle, this is going to be stronger, which makes sense intuitively. But keep in mind that this algorithm doesn't know anything about there's a substrate or not. So that's already kind of very neat that it can do that. And then you can kind of notice the other ones. So blue crosses look like they're always on the particles. And then the red X's, for the most part, are kind of like in between particles or at the corners or something like that. But already kind of did a pretty good job. And again, I'll note that these are from the, where we go? The test features. In other words, the network didn't see these to begin with. And so, it would be one story if we're just showing what the network already learned, but we have never even shown the network this, and it can show you where these features are in real space. So it's actually very nice. So can we now use this to predict anything? And so again, we did not show the network any of these test features. So if we use this trained model to predict, and this is just a predict method from this VED model, we get a prediction and a standard or prediction mean and a prediction standard deviation. So I'll just show the prediction itself. And so again, what does this mean? So the feature itself, features test, is a stack of these image patches. So the network never saw this image patch on the left, which is number 10, whatever. We have the ground truth. It's this noisy blue curve here, because again, all of this is pre-acquired. But upon prediction, and again, prediction of what? Predicting the spectrum at the center of this patch, and it looks like that. So it's actually doing a pretty good job. We could play around with the other ones. I think that one actually did much better. Maybe I should have started with that one. And so you can see how many features of tests there. So there's 400 of these. So this can go up to 423 or so. So you can kind of look through all of them. There is a way to see how the entire space prediction does. You can compute kind of a mean squared error for this, and then do that for every single pixel, and then get some kind of error map. I won't really go into that, but it's possible if it's of interest. But anyway, I mean, point is, it did a really good job of predicting. Let's do another one on it. 111. Let's see how you did. Okay, not too bad either. So it does a pretty good job, and that training was pretty fast also. So image to spectrum, pretty good for a variety of different geometries. And I'll emphasize again, this image patch was never actually sent to the model. So this has never been seen before, and it's predicting quite a good job, I would say. In a sense, it even denoises that, which is natural to these encoder decoder type of models or network architectures, is that you kind of reject the noise anyway, so you kind of remove it. So that's actually a useful feature in general, but it does a very nice job. We can further look at this so-called back projection, and I think this is the part that might not be shown right now on the the GitHub version, but we'll add it later. There was just a typo here. Anyway, it's the same kind of thing. Z here is that's what we're using up above. Where is this guy? Real quick, I'll just show here. So when we use the model to encode the feature tests or the features here, we're getting the kind of the latent features, which are Z, and then we're plotting them. So I'm using the same Z here as I am down here. This one takes a few seconds longer than the other ones, maybe. But in a minute, we'll see. And I'm not going to run the second one, it's already there, but you can play with that. But we can kind of see now some sort of like distribution of different features in the sense of image patches in this case, and how they kind of organize in this latent space. And so how are they described by these two latent dimensions, kind of Z1 and Z2, which what their physical meaning is anyone's interpretation really, kind of difficult to articulate, but you can see a distribution of different image patch shapes and geometries and so on. And so we can do the Spec projection again, and this is kind of similar to the manifold anyway that is shown above, and kind of see this distribution of different spectral features now. So far, okay, that's very cool. But I'm going to skip the error mapping. Okay, this part, and I'm going to drop this to 20. So this is, okay, latent dimension play. All of this is doing is it's repeating exactly what we just did, except we're specifying latent dimensions here. So previously it was just 2. We could choose however we want. I mean, I think of this sometimes as like number of components in some like NMF or something like this, but probably it's not the best way to think of it, but it's just a knob to turn how many, things do you want to use to describe what's present in your system. 10 is probably too much. I'll say that, but it's interesting to see what will happen. And so we can run this. So again, I'm calling it, instead of VED, it's VED 10 for 10 latent dimensions. And so then we're initializing. So everything is the same here, except actually I've reduced it to 20 steps, and it looks like it's reasonably converged. And okay, so we can again do this encoding, but in fact, let me do this separately really quickly. If we look at the shape of this, there's like 423 because that's how many test features we have, but then there's 10 10 for 10 dimensions. So we can't do what we did before when we just plot Z1 and Z2. We can just choose where to do this. Okay, so when we're doing the scatter plot in latent space, I'm only looking at latent dimension 0, 1, and 2. So the first 3 latent dimensions basically here. And that's what the structure looks like in those dimensions. We could look at, 4, 5, and the 6 because there are that many dimensions. And so we can start to look at, a bunch of different things. So visualizing this is very difficult and it probably doesn't help so much to just look at 2 or 3 dimensions here. It's very difficult to understand these higher dimensional, visualizations and so on. In any case, we can still do the clustering though, and in the same way, using all of the dimensions. Whoops, I didn't mean to. What happened here? Oh, okay, here we go. Okay, visualizing the clustering again is weird. We can visualize them in 2 dimensions. In this case, the first 2 latent dimensions. There's some, yes, they cluster. Actually, that's pretty nice. But you can look at it in 3 dimensions. Maybe there's some clustering there, and so on. That's not really critical here. It's just, a point of us attempting to kind of understand what's going on in this 10-dimensional space. But the important part here is really we can then map these back to, these, or get the centroid or the center of mass of these clusters and then map them to real space and see what they look like. And actually, there is some difference already. There's potentially like a short range edge feature and a long range edge feature. So if you're really far out into off of the sample, you have one thing. If you're closer to the edge, you have another. And that closer one is actually same as this whole, and so on. And so learning maybe potentially something a little bit different. And so we can also predict on that. Again, the difference here is using event 10 for 10 latent dimensions. Let's see how this one goes. Maybe that's not a good example. Well, in any case, somehow this was much better. Generally, the prediction is not actually that improved. It might be for going in the opposite direction when we look at the spec to N, and I'll touch on that briefly. But the point here is that really, if we scroll back up to, let's go to the beginning of, or the end of the original, let's say, what is this, 15? Oh, that's gonna be wrong. Well, okay. Already, this is 2 latent dimensions, and it's doing a really good job, I would say. And so if we go from 2 latent dimensions to 10, and there's not really an improvement, then we never needed to do that effectively. And so that's kind of trying to over describe it, trying to train it effectively too hard. If there is some improvement, then that should be considered later, but there's not really a big improvement here. And so I would say it's probably not so useful to do, just don't throw 100 latent dimensions at this just to try and describe it better when you only need 2. You can even understand the latent space now with 2 latent dimensions. It's very nice to visualize, and you can have a more maybe intuitive understanding if you stare at it long enough. But 10 is a difficult one. And so the point is that is another knob to turn. So far we've got a few knobs. It's the window patch size and number of latent dimensions, and so on. So anyways, so that's the im to spec. This is spec to im is not there still on the GitHub, but we'll just upload it. It's not using the PyroVed. I don't believe the PyroVed has spec to im, or it's not quite the right model architecture for spec to im. But we can kind of custom build it here, which was done in the original paper anyway. So there are just a couple of convolutional dilation blocks, just building the network itself. So this is kind of what's under the hood. I wouldn't say this is too important, but what is important is we can do the same Sally. So you may remember this from before. Features and targets are the patches in Spectrum. We do some normalizing and train test split. And these are just kind of the initializations that were done under the hood for PyroVed that we're doing kind of now right in Torch itself. And now you might notice that the feature size and target size, these things are just inverted from one another, or they're swapped now. And we can do all the same specifications, kind of number of latent dimensions, number of epochs, and so on. And then this is kind of the loops that will run the spec to im. And these ones take about 10 seconds to train. So maybe I'm not going to wait for that, but you can play with that on your own. But when we go ahead and do a prediction, so this might take a few minutes. Okay. You'll notice, so keep in mind, again, with this train and test split, we trained on 80-something-5% of the data, but then these spectrum here were never actually seen. And so one of the things that we might think about doing is, this is, all of the data for the training effectively was a little noisy here. And so potentially we can denoise it. I mean, yes, it's kind of denoised itself anyway during the auto-encoding process. But then when we want to do prediction, it might not make sense to use a noisy spectrum. So that's just some kind of consideration that should be probably thought about. Anyway, if we don't treat anything like that, we just use the test data now. So this is one of the test spectrum that were never seen. The ground truth is on the far right, and the prediction is in the middle. And so it actually kind of did a decent job of realizing that this spectrum, particularly if you notice, let me go back up to the NMF briefly. Is it the NMF I wanted to show? Yes. So if you look at kind of the green spectrum here, there's no shoulder. And so that shoulder tends to indicate that you're very close or on the spectrum. And then the energy shift of these also is another kind of feature. So you can kind of think about, maybe this network is learning something to do with, okay, there could be the intensity of this main peak, I would call it, the energy of that main peak, and then potentially if there's any shoulder structure. So that's just a simplified description of what spectral features might be present, but we can already understand as human that, okay, there are differences that are more or less obvious. And particularly when you're directly on a particle, you have an extra peak here at the bottom right here. So there's that to be consider that as well. So going back to the training, so the training is done anyways, so we can then predict. I'll just repeat the same thing. So you'll notice that there's no real like shoulder in this case on this test spectrum, and so it noticed that maybe the intensity isn't as strong. So if we are further away from the particle, this peak will be weaker. So maybe that network realizes that there should be less and less of some sort of edge intensity here. So what's very peculiar in this data set, however, is that this spectrum here should not have been able to predict that the particles were on the left side. So notice that this is really just, you're away from the particles at some distance. That's really all you should have been able to get from this spectrum. But somehow it knows that, or maybe it just got a lucky guess that the structure is on the left. Yeah, it's not exactly the right structure, and there's some gaps between particles, but it somehow realized that it's on the left. And so how is that even possible? Well, I don't have an answer for you, but we can start to look at different, let's see, different tests. Again, another one on the left, and again about the right distance away. So something actually very peculiar is going on here, and that was kind of an unexpected result. We think this is because of any slight tilt in the specimen. You might be picking up different spectral features that are more sensitive at that tilt, and so just because of the tilt, you may be able to resolve some of like which side of the structure are you actually on. So that's actually a very peculiar and curious thing here. But anyways, back to the real world, I guess. We can then, look at a bunch of different of the test spectrum and find that how good did it go. Then we can also project this into the latent space again. Remember, this was trained with 2 latent dimensions. We're back to 2 now. And this is the distribution of the test features in that latent space. Again, we can cluster it. In this case, I'll cluster it a different way with the Gaussian mixture by specifying that we have 4 clusters that we want. We can change this to whatever we want. This is kind of like how many components do we expect to be in the system, but it's nice, reasonable clusters here. We then do the same kind of encoding and so on that we did before to kind of get these are the so-called like centroids of these 4 clusters. So before we had like the 4 spectral, or I guess it was three spectral features that corresponded to the center of mass or centroid of each of these clusters. Those were spectrum, but now we're doing the spec to im, so everything is reversed now. And so these are the 4 image representations or image components that we have kind of that are encoded in this data in the latent space. And so they may not look like sometimes anything physical or like something that's not particularly or explicitly represented in our data. But I mean, this one looks like an edge. Maybe this is at the center or the intersection of like 4 different particles. Maybe this is a hole. So you can kind of get creative, but it's kind of interesting to see what this is learned. We can also see what the corresponding spectral representation of these 4 features are. So edge 1 looks like edge, and hole looks like the main peak is the strongest. So these are all on the same scale. I mean, you have to look at the scale. And so, okay, there are some features there. And then finally, we can then look at how those project into real space everywhere. And actually, I guess I forgot to mention, when I did this, when I'm looking at the latent space distribution here, I'm actually using all of the targets, not just the test ones. We can look at the test ones in this cell, or if we uncomment that out here. It's just kind of more interesting to look at all of them. So when we do that, you can see, oh, hey, we have kind of 4 features here. I mean, we decided that there were 4, but they're very well separated actually, and that's kind of interesting, I would say. What else? And then finally, we can do this back projection again into latent space, and this one, similar to what I showed in the lecture, shows what we've learned from this, the image representation of this back projection, what it looks like, and it's a little bit more diffuse than when we do the IM to spec, because we're starting from an image and going to a spectrum. It's just naturally, like, information limit is a little different here, and so it still learns something though. So that's kind of useful. And so I think we can do these error mapping. I'll skip that here, but really the final thoughts I'd have here would be, okay, what happens if we change the window size from 16 pixels to 32 pixels? Are we learning something different? Similarly, if we drop it to 4 or 5 pixels, something different come up. Spectral binning, which is spelt wrong, it's frustrating. Okay, so the number of pixels in a spectrum is something like, this is your feature or target size, depending on which one we're looking at. So there's like 1024 pixels in a spectrum. That's probably too much. So we can bin this to probably something like 128. It'll probably also improve our training speed, and maybe even like help denoise things a little bit. So that's something to consider here. Number of latent dimensions is the other one. We tested that with 10, particularly with the spec to in. When we do this last one that I did in the paper anyway, we found that when we increase the dimensions more than 2, but I think it's kind of diminishing returns after 4 or 5. When we did that, though, we did get a better prediction, actually. And so that's kind of an interesting thing. So potentially something to play with here. And finally, the data pre-processing. So what I did not show, and I potentially can have that on request, is how we're getting, the zero loss peak. We're always typically having that. How do we get rid of that? How do we do the background subtraction and all of these, like, alignment of all the zero loss peaks? And there's a bit of pre-processing that goes into here, which potentially could have some impact on your final result, but hopefully it's not too much of an impact, as long as the fitting is reasonable. But in any case, and then there's just other, you could select different spectral bands for describing your spectrum. Even if you bin this to 128 pixels, as I mentioned, there's still 128 so-called features that are describing your spectrum, just at an intensity or a count and an energy channel. But do we need that many still? So maybe we could even reduce that to something like human described, like, oh, peak intensity really at, you could do some peak fitting even and describe it by just like a 3 Gaussian curves, and their spectral or their width and their intensity, something like that. You could describe the entire system that way, and maybe that will be easier to learn. Or maybe you're throwing away something important when you do that, and so maybe this network is actually picking up on that, on those details that you might not even think of. And so these are kind of the thoughts that I'd leave you with. And so there could be others, and I would encourage you to play with probably the window size is the easiest one to start with. And then maybe even latent dimensions as well. And then other data sets, there's 4 in here, remember, and I'll just put this at the bottom here. So we have data sets, and you could look at the keys. So just a dictionary of data sets. And so I'll just data sets, let's say we looked at number 1, I believe. So if we look at 0 and we look at the hat of 0, it's something like that. And so this is the same material system. I think the concentration might be slightly different, but I would say that the shape is different because the concentration is different. So potentially this could be grouped with all the same, libraries, so to speak, and we could learn something here. And so, it's the other one. I thought there was a cool one here. Might be a little difficult. Yeah, potentially something here. I would probably say the next one to go for would be this 0, data set 0, which this guy is here. So maybe something could be learned here as well. And so And then don't stop there, use your own data if you have anything else, or Sergey has shown this SEM data. And so it doesn't need to be STEM eels, access to some of this data is it's non-trivial, I'd say, sometimes, especially for this monochromated stuff, not easy to get that. But in any case, this should work. This autoencoder scheme or encoder decoder should work for a variety of things to learn these structure property type relationships. And with that, I think I'll hand it back to Sergey and see what he has to say.
Sounds good. Thank you, Kevin.
Yep.
So in the remaining let's make it about 15 minutes, let's have a quick look at the dual VAE setup. So in this case, you will have an opportunity to see what really happens under the hood of more complex models. And one thing that you will notice is that generally when we start in this course with the basic principles and simple image analysis, we use the functions that have been developed through multiple iterations. And essentially, they are now very easy to use. So these are the tools that are reasonably well understood, that have been tried and tested for a variety of applications by literally tens of thousands of, if not hundreds of thousands of scientists over the time. Once we get deeper into the weeds of the machine learning applications for microscopy, we start to gravitate closer to the outer edge of what has been developed. And when we do that, we start to deal with the codes that are they have been developed and tested, but they have not been optimized through the tens of iterations. That being said, these codes allow to do things that simply have not been done before and has not been possible before. So the IM to Spec and Spec to IM that Kevin have shown is one example, but let's look how the dual VAE is realized. So this is, as I mentioned, this is a new architecture, and what it does is that we have essentially two autoencoders which are sharing the common latent space. And the trick here is that the way things are done in the latent space is not a rigid alignment of point to point, but application of some sort of linear transformation that basically tries to map these latent distributions as close to each other as possible. Another kind of unique thing is the addition of the rotational and possibly translational invariants, which allows us to deal with the objects which are the same but have different orientation in the image space. So as advertised, this work has been published, and as the case for all of our work, there is a copy on the archive in case if you don't have access to the this particular journal. So let's see how things are looking like. Notice that the convenient thing about the collabs is that we don't necessarily have to visualize what's actually happening under the hood, but in this case we can. So we can look at the code that realizes the dual VAEs, and you can see it's kind of pretty large amount of code. So there is no way we are going to go through it throughout 20-minute summary. So let me just mention that the code is written in such a way as to define the classes that we need in order to run this specific type of the VAEs. And if you're familiar with the PyTorch, you will easily recognize what this code is doing. If not, then the important part is that it's work, but maybe not exactly how it works, or not exactly how. So let's close this part. We also have some additional functions here that allows us to perform the hyperspectral image analysis. So these are custom functions which are written in order to filter the data set, in order to create the hypercubes, and so on and so forth. Again, if you are interested in exploring this type of approaches for your own data set, this is something that you need to have a look at to just have an idea about what happens under here. If not, then you can use the notebook the way it is. So after that, so let's assume we don't see this part. What we do is we download the data set, and then we repeat roughly the same type of operations as Kevin has done. So we can load the image and data. We can have a look at what the spectral data look like. So there is a large variability of the system behavior. We also have the ground truth labels. So that was a part of our data that we give to our network. We convert everything to the torch format, and we reduce the dimensionality of the spectral data because it's kind of a little bit too much. And this is what we are left with. So this is an array which contains our imaging data. So we have 327 images, which are each 96 by 96 pixels. And we have equal number of spectra, which has 52. So we kind of considerably reduce it. We can easily visualize the examples of the data. So this is how our images look like. So this is, as you can imagine, was a large number of SEM images to acquire. This is how our spectral data look like. So for spectral data, the difficult part was to make sure that they aligned with the SEM images. So then we create our dual autoencoder. So again, we are not going to go through the details because it will take for quite a while, and you need it only if you either want to improve the code, but not necessarily if you need to just use it as it is. The important thing is that we have the option to transform our coordinates, so to do the rotation. That part is important and fairly unusual. So you will not find it in the standard implementations of the encoders for normal problems. And then we kind of can have a look at the what happens, how do we create the VIEs with the enforced similarity between the latent spaces. So again, we need to write the function that will allow us to train it. And the way we do it is we have two objects, so structure and image. And this is how we do it. So we send the structure through the first encoder, get latent representation, compute the Kullberg-Leibler distance from the Gaussian, and then decode it, compute reconstruction loss. So same way as you would run a normal autoencoder. You do the same for the spectral data set, and then you define the transformation from the linear transformation for Z2, and then you create the compute the score that determines how different are the encodings for the spectral and the image data in the latent space. So this code explains, kind of goes through the details of how it is done, or realizes how it is done. So, basically, again, there is no way to go through it in 10 minutes, but if you decide to apply it for your problems, you should be able to use the code the way it is now. And then once the code is written, we kind of revert back to the usual way the PyTorch works. We define our image data and spectrum data. We create our data loader, so something that feeds the data into the network, avoiding the problems with the memory and so on. And then all we do is to train the model in the usual standard optimization. So once we do that, this is our training. So remember, I told you that this model can be trained with very small amount of data. So if you notice, our image patch is actually 96 by 96. So they're almost 10 to the 4 dimensional. At the same time, we have 300 examples. So this is a situation which is actually opposite to the big data. So it turns out that even in this case, we can train the autoencoders and these dual autoencoders. The trick is actually to train them for a long, long time. So in this particular case, we were training them for 20,000 iterations. And it turns out that there is an interesting behavior that the loss function first decreases and then it kind of shows several oscillations. So it seems to be the case that, at least for the examples that we worked with, we really need to be here rather than here to have the good training. We don't know why. It may be this case of the dual overtraining that people have discovered recently, but that's a finding. Then we can look at the individual losses and see how they behave. So some of them are gradually converging, some of them show the same type of dynamics. And then we go in the usual way to encode the data in the latent spaces. So we can look at what happens in the latent space for the both structural and spectral data. We can do the same type of the test data and see how they are distributed for SEM data and for spectral data. We can play with the manifolds. So this is the same manifold that I've shown in the presentation. And this is the manifold for the spectral data. And we can try to run the image spectrum prediction. So this is how it is realized. And here you see that this is the case where we take the image and predict the spectrum and compare it to the ground truth, and take the spectrum and try to predict the image. So same type of things that I've shown in the PowerPoint presentation. Then we can do the same type of analysis for the full data set. So same approach can be used to train the VAs without enforcing the similarity. So in this case, if we go through all that, you see that one converged, the other did not. So the spectral data was able to find a good latent representation. The structural data, the spectral data kind of collapsed. So the primary thing here is that this is obviously a very short view through this notebook. The important thing is that whether you can use it for your own data sets. And the answer is you can. So all you have to do for that is to create the structure property pairs. So the one data set is image, another data set is spectrum. And you need to bring it to the same format as used in this notebook. So if your data is in the same format, this approach will work for your applications equally well. So I've posted the notebook on the course GitHub repository, along with the notebooks for the Tuesday lecture. So again, feel free to play with them. Remember that they're useful only if you apply them to real-world problem. And let me know if you have any questions. So if not, then let's call it a day and see you all next week. Thank you, Kevin.
Yeah, thanks. Bye.